So
Is it recording?
Okay, let me share screen. I think it's
Hold on a second. Yeah, is it recording? Does it say it's recording?
The light's on, yeah. It's flashing
Yeah.
in the
Yeah.
cloud.
Cool. Gotcha. Man, we're doing stuff in R today.
yeah. So I when I started
I needed the next one down.
sorry, okay, so
Yeah.
so I wanted to do instead really because it would have been an opportunity for me to learn it as well. But when I struggle with even importing my data, I had to watch videos to import my data. So I know it's going to be a short journey trying to do everything. So I kind of turned back to this because I'm more comfortable with R source. Yeah. So, but before the tutorial is complete, I might try to take it up as a task, also do the data equivalent. So that would be
So you've worked more in R than,
more in SAS and R.
yeah.
I never really used data like I couldn't even get in my bed. My data I had to start watching video about it. And I was happy I made this chance to work with this because then I could look into the codes and I try to understand what they are doing. That would have been quite difficult. So you all do bear with me. I know. Do you have R installed? Yeah, you do.
I do.
Okay. So I'll just try to go through. And some of these packages, maybe I should have run it earlier to save some time, but some of them might not really go through because of version problem. So, but if you have the code, you can just run through. So each click, I think that is the way Stata works also, right? Each click goes through, runs a line of the code. I'm just going to run all through all of them, so it takes time.
So you got all these packages from their website?
Yes, from their website and so some of them are not on the website because some are sub packages inside the ones on the website. I'm trying to get to the slides too.
Oh, that's fine.
So my work was made easier for two reasons. One was the resource pointed out McGee and the websites. Most of these the code are essentially from their website. But what I was trying to do was to modify them in a way that will force me to understand what they are doing. So the modification was very minimal, but it's more or less like changing the keyword they use to something similar to what we are doing in each section. So the first three, yes, it's from their website, and then they had two other ones that occurred while I was trying to run the program. Okay, so it's on Head Start, and it's the same data and the same paper we just went through. So I believe like part of my challenge was understanding the RDD part very well. Was it's still not very clear, but because most of these are just functions they've written already, so it's easy to actually just implement it. And sometimes so I could do this, but that does not translate to actual understanding of the process going on behind. But we've talked through the paper, and so I hope that reduces the concern on the reality. So Head Start started implemented in 1965, and this author here, Ludwig and Miller, use RDD to kind of analyze the data to estimate the effects. And just as Dr. McGee was saying, so they had, and I saw this as a light drop until that conversation. They had 33 to 50% drop in mortality rate. But then one will begin to ask, what does that mean in practical sense? Like, what is the practical significance? But in percentage, that is very huge, right? Yeah. So I more or less essentially, I mean, I essentially reproduced the paper we just went through. So we see a lot of those graphs today. So there is two sections. One section is sorry, that should be verified, right? Verify that RDD is appropriate for the data. And then the second session will be, of course, the inference test. So under this, we start by plotting the global, using all the data plotting to show whether there's discontinuity, and we talk about all this test. So I'm just going to go straight. Listed the packages here. These are the one we just installed, and some of these functions. So some of the packages and the functions they use have the same name. So you install it as a package, but you still use it as a function while we are running. Okay. So we start, of course, with the first plots that they have, kind of showing the discontinuity. So let's go back. Let's go to R now. Here the packages are installed. So this section of the code just clears the database. I mean, if there are data that were used earlier, it kind of takes it off. And then R, of course, loads. So after installation, you load. I don't know if you said that also. You use this set of commands to enable the function become active. So the first will be,
which is the RD, just real quickly, I was just looking at, so you're none of the libraries that you're loading local rand, RD robust, RD density, and sandwich. Okay.
Yeah. And so the other ones, I think as I go along, I also like bring them in.
Okay.
Yeah, along the way. So I kind of, so these are the first few. Okay, local rand will actually be used for randomization inference. So I think RD density will be the first one to use. And the sandwich is a kind of sub program. So if you see here, we did not load it here. But if it was not already installed in R, it would have given an error message when I run the library, right? So it's some of them are sub packages inside this, like this RD density has oh, it's not even here. It has RD bandwidth select, RD bandwidth. So there are two bandwidth functions that is inside that list. So these few will enable us get started, and then we can load the other ones as we go along. So this function here is just to bring in the data. Should open up a little window somewhere. I'm not seeing that. Okay. You want to okay. So that's it. Okay, so we are still doing it. Let's do this. Okay, so it opens up this, and with this we can navigate to the data. Okay, so once it's in, dimension shows the number of rows and columns. Names brings out the list of variables. Just the variable names.
Hey, GK, I wonder if you could, if it would be quick for you to email us your code and those data.
I actually did it, right?
Yeah, we got them. I'm not sure if it didn't go to. You already did, huh?
Yeah. So
awesome.
Yeah. So I made mistake. I mean, it wasn't this. I sent to him. It was the second one.
I see. Sorry. Thank you.
So, okay. So and I'll be going through the code intuitively, but if there's anyone you want me to explain more, just let me know. So this is actually where the analysis started. So the first thing that was done here was that this variable, which is the variable of interest, like the outcome of interest, was assigned to the vector y, right? Then this is the running variable, like the raw version, like the way it is across all counties. But over here, of course, is the cutoff selected to be at. So this is all of the variable, like every one of them. So if I select this alone and execute it, you have 1821 remaining, right? And this is about 1000. So this is about 2810. So it's everything that comes in there. But the only variable that comes in there will be just poverty rates for 1960 across all the counties, right? So then the cutoff was selected to be 59 points, approximately 60% death rate, mortality rate. I'm sorry, poverty rate was selected as the cutoff. And so if you subtract, so this was just like balancing it, centering the data, sorry. So let me be sure we have this. So if you subtract the cutoff from the entire data, so this will like picking up each of these variables and subtracting cutoff. So you essentially center it. So the mean will be, the mean of this right now will be 0. All right. Will it be 0? Yeah, I think. So essentially this centers it. So if there's a cutoff, if there's a poverty rate that is exactly 60, then of course the mean will come out to be 0. And what this next line does is that it creates the treatment assignment. So for every value, so let me do head here. So head will show me the first few variables, right? So these are just the first 6 variables from R, right? Remember, R is the centered version of the running variable. So for every variable, this line will be for every variable in R, every one of these centered variables, if it's greater than 0, right? So because once it's centered, the mean will revolve around 0. So if it's greater than 0, it's assigned to the treatment. If it's less than 0, it's assigned to the control. Right. So this essentially creates a dummy variable 1 and 0. True. So if we run only that, we see a bunch of 1s and 0s. So it just went through the entire data sets using the centered value and assigned 0 and 1 for those that are above or below the cutoff. And I think I'll just move forward maybe quicker. Okay, so here is where the implementation starts. So they didn't include this one. I just included it to show the initial plot. So the first line kind of subsets the variable, or the variable, like the outcome variable and the raw poverty rate, wherever they are not missing. So this exclamation mark means not missing, right? Wherever they are not missing, that is created as a subset and stored inside II. Okay, so that's what we have here. So from within II, I am plotting the raw variable. So this will be the raw poverty rates across all the county. Okay, plotted with the outcome variable against the outcome variable. All right, and so we see that figure. So this will be like using all the data sets.
I see what you mean about zooming in, huh?
Right. So we see everything is clustered here. There are just, so what they did in the next is to kind of, cut this off. Okay, so this is not their final code. I was producing these different codes to kind of show the process. So this code here, this one could reduce this to 3000 beans only, right? So the graph will look a little different. So if you run that with 3000 beans, we have this. So this is section of their code. So what is happening here is that we have this RD plots. the RD plot is one of the functions under the RD density plot. So it automatically produces the regression lines on both sides. Right? So this is binned to 1,000. So if you compare it to the other one, this is very clustered here, but they binned into 3,000, sorry, and they have this. And the continuity wasn't very obvious yet, right? So what the next line of code did was that it cut off the outcome variable at 20. So it's like coming over here and cutting off from mortality rate of 20 and zooming into this small portion. So when that happened, you have this other one, right? So we are moving in and in into the data, and so we are seeing more clearly the discontinuity. So, but I was wondering at the subjectiveness of this, like, ordinarily, if I didn't think, it's like I'm looking for discontinuity. But if I look at the first data, it will really be difficult for me to see that there is any. So this is the final implementation. So this is the one where the function actually worked the way it works. So what this one does is that it bins it, just as you was explaining, based on evenly spread bins, based that it makes the variability in the data. Right, so it's automatically chooses the number of bins and that mimics that and averages it and puts it out in a way that it becomes clearer where you actually have the discontinuity. And this was the graph I had about. So with this now, it's clear that yeah, there's discontinuity, but I'm thinking just as a researcher, I pulled some data and I saw this. I don't know if I will be able to project to the fact that that's not going to hide somewhere there either. So, assuming they didn't know that this guy used RDD to do this paper, would they have picked this paper and gotten to this point? So
that's awesome. So the default in RD plot is evenly spaced?
The default is evenly spaced, actually, that means the variability of the data.
Gotcha, that's interesting.
Yeah, that is their default. So they have that on the paper.
Because this is exactly what's in that paper.
Right.
Yeah.
So yeah, just to look into the data, I was not producing these other ones to kind of see when they go.
Yep. And I'm guessing you could just type in, there's some easy way to have an option here to change it to be quartile based or
right. So if we do question RD plot, so this arrow is, I don't know if, I think Stata should do that as well. Arrow is handy at using this to get the details of the function. So,
perfect. Yeah.
So we could see bin select scale can with trying to see where they are that.
Don't spend too much time on it.
Okay, so it should be one of the big selections.
Yeah.
So there should be an option to change that.
Oh,
Then the function, the entire range of what you can do is already. That is a lot. But most of them are set at the default. So if you just have the cutoff variable and your outcome and the running variable, it's automatically means that plot for us. Okay, so after that, so there's evidence that we can use RDD, and then they conducted some falsification tests. Let me get to the slide and see if that's the next. Yeah, okay, so the first falsification test is the binomial test, right, to show if the data will actually assign as is expected as a binomial distribution. So this was just a sequence of codes that illustrate that. I'll go to that very quickly. So the first part is to create an array like a holding space. So this is where if you think you need, okay, so this first line here shows the randomly selected bandwidth, the initial selected bandwidth, a window, right? And they are increasing it by 0.2, right? So it goes from 0.3 to 1.3. increment of 0.2. So if you check that from 0.3 up to 1.3, if you are increasing by 2, you're going to get six different rows, right? And then we are hoping to put in 4 different items on the column. So essentially what we're trying to do, we produce this table. So we have 4 columns and 6 rows. And that is what informed this first line. So this is just a placeholder for those values. So if we run this, and let me just reproduce the actual outcome. So right now what it does is that it just has the table already there, but with placeholders, right? Then we begin to generate value into those tables. So this tells it what row to be working on. And then in this function now, this is the window, it will flow, it will be a loop, right? Starting from 0.3 all the way to 1.3 at increment of 0.2. That's what that first line is doing. This second line is trying to assign, match, okay, subset data that fall within that window. So remember, R is the centered running variable, right? So this code here will check that centered running variable versus the window. If it is within the window, it assigns it to this value here, right? And then this line takes account of how many data that comes into that variable. So this will take count of where you have the control, right? And this will take count of where you have the treatment. Okay, and then so D is 0s and 1, right? The assignment function. So if I actually have a value here on this window that falls into that window, and I multiply by 0, this is going to become 1, right? So for wherever there is 0, this will take account of 1, and it continue increasing. Whenever there is 1, right? If D is 1, 1 times whatever I say will be 1, and 1 minus 1 will be 0. So this effectively takes sum of the control group, and this takes sum of the treatment group. Okay. So that is what this 2 line is doing. And then this line is conducting the binomial test. And in the binomial tests, as an add function, you need the number of success, the number of trials, and then the probability of success. Okay, so we are using length, the command length DW. So this is supposed to be the count of treatments. So the length captures that number of data sets or number of items that fall within the window. And this captures the number of successes because this is treatment. Okay, so probability is set to 0.5 because it's 2 outcomes binomial. So finally, we have the p-value extracted. So this binomial test is put into temporary file, and from that temporary file, you have the p-value as one of the elements that you extract. Okay, and then of course the row increases by 1, so it goes to the next row. So that loops like 6 times, and that's how that table gets produced. So let's run through that. So this is a function, right? So it will execute as a chunk. It starts with this curly brackets and ends with that. So it's good thing that we're able to see what is going on inside here. So they didn't have names on that. I was adding these names to kind of make it clear. Because right now, if you produce that table by this last line, it's going to just look like this. Right, so I wanted to know what are the columns and that, just to make it more specific. Because we have the paper, which was very useful, it's easy to match the code with the names. So I added those names. So if we run this line before that last one, we now have the table reproduced. Right. Okay, so the concept for me here was, how do I choose the window? Like, what's informed them using 0.3? Where will that come from? So I tried to play with it. Say, okay, what about if I go further down? If we use 0.1 instead. So we've increased this by, okay, sorry. I think the number is, okay. So if we use 0.1 instead, so we've increased this by 1 point forward. Okay, maybe let's go further than 0.1.3. Let's go to add one more point because we're increasing by 0.2. So 0.2 plus 1.3 will give us 1.5. So we've added one before. So on this table now, added one on top of this row and one below the row to just see how they will behave, right? So because of that, we're going to supposed to increase this to 8. We just added 2 more rows. So the first number there is 0, the second is the column. We still have 4 columns, so we're going to leave that as 4, right? So let's run that and see. So what you see here is that it's like they are picking a window that is so small enough that it's 100% certain that it's binomial, right? So if you go smaller than that, it's still one probably still 1. So there's really nothing you're getting, right? And then, so that could be easily taken that maybe by trial and error, you find out the smallest window will have probability of 1 for the first time, and then that will be your minimum window, right? And then you continue going down. So look at the next one we added, 1.5. It's not changing much anymore. So if we add another one, they are just around that 2, like kind of remain stable. So they are picking the widest window that gives somehow big considerable p-value, right? And then they are making sure, of course, they are moving away from the one that is certain. Everything is binomial, right? And then they expand. And so that was helpful to know that you can play with this and decide on what will be your minimum value and the maximum this range. Okay. So that is how this table, the binomial test was conducted. And of course, so you are focusing on using a window that is within where the data is binomially distributed. So the idea of which one is optimum here, without judgment be based on the one with the highest p-value.
I don't know that you can really judge it here.
Sorry?
I said, I don't know that you can really judge it here, can you?
Okay. Okay. So like saying what will be the optimal. So this, oh, okay. Yeah, but so this is testing different windows, right? Yeah, different bandwidth. So if you have to choose one from these bandwidths, right? Anyway, okay, so that's not the purpose of this test, though. That was saying like this.
Yeah, I don't think
is
it's-
just to classify.
Yeah, I don't think this is really the purpose of this test. I think the purpose is to, as you said, also it's seeing,
Right.
you know, where does it break down where you don't really have kind of balance between treatment and control observations.
Okay.
Because, you know, in these data, as you expand the bandwidth, the control group is going to grow much faster than the treatment group.
Okay.
And so you end up with ratios that are just way off. Yeah.
Okay.
Like if you ran it, I'm guessing even much larger than this. So if you did like a bandwidth, I don't know, do a bandwidth of whatever, 10.
Sounds. Okay, so we have to do some maths here. 1 to 10, right? Starting from, okay, yeah, 0.1 to 10. So maybe 10 minus 0.1 divided by 0.2, right?
Yeah.
Because when we figure out number of columns, otherwise
Yeah.
the code will not work.
Yeah.
Can we do that?
So 10 minus
0.1
divided by 0.2,
divided by 0.2.
49.5.
49.5. Okay, let's do for the.
Or you could just do in your sequence, you could just do
By
1 to 10 by 1.
Sorry?
You just change your sequence to go instead of from 0.1, just delete the point, do
Okay.
1 to 10,
Oh, okay.
change it to by,
Okay.
and then do by 1 on
By
the,
1 increment. Okay, so that would be easy to count then.
yeah,
So we'll make this just 10, right?
Yep. Perfect.
Okay. So let's okay, let's run this and see.
we're spending a lot of time on this. particular- We're coding.
Okay, so this is the table.
Right. Right, all of a sudden you start really expanding that control group and you start rejecting.
Okay. Oh,
Like
okay.
7, yeah,
Okay, it's okay, okay. So you start rejecting more and you don't want to get to rejecting, right? You want to stop somewhere you failing to reject.
yeah.
Right?
You start to get really unbalanced after like 5 or 6, yeah.
And their bandwidth in the paper was 9, right?
Yeah, correct.
in the original, not the.
Yeah, against this paper.
Okay, so,
Cool. It's at the bottom.
is at the bottom. Okay. So that is the boundary test, the binary test, and then this is the Macquarie test. I think yeah, this person here, January, that. So it is the RDD package, which is also a function. Okay, so we'll just kind of load that. And so this needs the raw running variable, not the centered one. Okay, and that is the cutoff, of course. So I left this to their default, right? So I wonder, maybe changing the name might give different impressions. So if we run that, so this was not part of the one they have in paper. I don't know if this is the Macquarie test that you could be implemented before now in the other class. I was searching to find one, so this is the one that came handy. Yeah.
Yeah, I think it's the same thing. I mean, it's in the window, it reports the p-value, yeah. It even, yeah. It even tells you how to interpret the test. Yeah.
Okay, so that is the
sorting. Okay.
that is often you turn on and off. So that is this one, right? So if you turn it off here, that test wouldn't show. I mean, yeah, just the plot, right? But the default will. This is the default. I don't know what the opposite. So we have to manually turn this one to show those tests. Okay, so that is that, and then the authors have their own plots for suspicion. So let me be sure this one is loaded. And then again, we are trying to create so we just did this. So we're trying to create this one, right? So this is the density test, the table, and then of course the chart that accompanies it. So again, just the same kind of calculation we did. You take out the number of rows and number of columns you need, and you create an empty array that will hold the variables. Okay, so this is the function here. This is their function. What it needs is just the raw data and the cutoff. There are so many other things you can also manipulate, right? But with these two, it gives you the table and value that we use for the plotting. So I'm going to run this to save time. So we've already created the placeholder, and then we run the density function. So it's highlight that this variable is missing. I think it just excludes those in the analysis. So what this does is to create the table. So this function here, so if I do RDD density. So the function we just executed. Oh, no, that's not what I should do. So what we just executed, start that in temp, right? So if we do names times, we see the variables that was generated. So what the next part is trying to do is to pick up values from here, right? So we have number of variables below, a number of data points below and above the cutoff. We have the bandwidth and so many other things. So, and this is picking it up, fixing it on the empty table, right? We already created an empty table, and that was the number of rows and columns was based on what we expect here. So if we run that and then run all the functions, essentially picking up the elements of data that was generated by this function. So that fills the first, this is for the first row. This is 111 or 2, right? So this is for the first row on that table. So that will give you the value on the first row. Then we do the second row, same function. So the difference between that, I think we were talking about that is, so this is unrestricted, right? It selects different bandwidths, but you can restrict it, then it selects the same bandwidth, forces the same bandwidth on both sides of the cutoff, right? And then this last one also restricted, but I think, I can't remember exactly how it's different from the previous one. Okay, so but the option here is, do you want the same bandwidth on both sides of the cutoff, or is it the same bandwidth, I mean, different bandwidths on both sides of the cutoff? So the first set of code here produces different bandwidths, right? So all you need to do is to have the density function, the running variable, the raw version, and the cutoff. You don't need any other thing, right? But if you need this other variation, like restriction, then you begin to add this. So this is like saying plots, and Dr. Magi was explaining that, like, plots fit in a polynomial on this side and on this side and take the difference as your bandwidth, right? And so that is just what is different. Every other thing is the same. So we're gonna run that. So this is the last one, the restricted one. So you have restricted as an option. Yeah. Okay, so this produces the table. Again, I added names to them, so it will be easy to read. So that is the table that they have here. This is the density table. And what we are hoping, okay, I think there's a mistake, so I don't know why there's an A. What they are hoping is that, you know, the p-values are all greater than, so you're not rejecting, right? So the next set of code plots the graph that follows. And they needed this other package. It's not theirs, but I mean ggplots for plotting graphs in R. And then this is the function that plots that graph by itself, right? So all you need is to feed it the variable. So over here you have the cutoff. So sorry, this is taking information from what you had in this table, right? It's picking up information from what you have in that table. So the way to do that is kind of reproduce that particular equation I gave you the table inside there as the first element. Then of course you have the raw data, the raw uncentered running variable. You choose your alpha and these other options, right? Add label and all that. So if we run the RDD density plots, it automatically produces that. Okay, so but you can vary the plots or kind of enhance it. So for all of them, if you have question mark the function, you will have attributes where it gives you the detail of what you can do, what you can change, right? So you can change the color, you can change the grade, and you can change the look of the things.
So how long it took them to write all this?
Sorry?
I said, I wonder how long it took the authors to write. I mean, the help is extensive too.
Yeah.
Even for their custom functions, the help is extensive.
Yeah, and that makes, I think it makes, I don't know if Stata has that function, it makes R easy to learn.
Yeah.
Because you can actually go down to, I think the authors are required to document every detail of what you did, and they put it into the package itself.
Yeah.
So you can easily access that.
Yeah. I just want to flag that you got 10 minutes.
Okay. Okay, so let's move very quickly. I think we are done with the falsification tests, right? We looked at a couple of them. So the next thing will be inference, and we can do this very quickly. So the first one is the flexible parametric regression design. So we're just going to try to reproduce this table, right? So I mean, the theories and the explanation of what contains is what we'll be going through class today. So again, so the array statement is normally used to create placeholder. So again, this first line is just creating placeholder. So that if you look at it, it's just placeholder for the number of rows and number of columns you intend to have. So here defines the column, tells it, controls the loop across the column. This is the number of the polynomial setting, right? So this will be for linear model, linear local linear regression because P is set to 1. So for constants, you choose 0, right? And for higher order, you can increase that number. But of course, they advise against increasing the number. So we run that. And then I will not talk to the loop, but it's similar to what we saw earlier. So this loop is just trying to set up your variable the way it is needed. This is taking care of every variable that you have within the window, right? This is taking care of only those that are in the treatment where your R is your center running variable is greater than 0. And this is picking up those that are in the control. And then, of course, number, this is count. And all that. So if we execute that statement, this is taking up the standard error to compute the test statistic. So if we execute all that, then again, the row names and the column and the table. So what I produce is just the first column where you have bandwidth of 9 and 18, right? So this variable, it is vertically positioned. Yeah, but it's just that. So I added the label helps us to know. So like the treatment effect is 1.8591. So that is what you have there, base and base, right? And then the number of counts, 300, 679 is 300, 679, and so on, right? So you pick up the numbers and put them in the right location on the table.
And this is done, so it looks like inside that loop, it's running that linear model.
Yes. So it is over
Can you
here.
just walk through that linear model real quick?
Okay, so it's right here.
Yep.
So this is LM linear regression for R. Okay, so that is the response variable, the mortality rate, the treatment assignment, and the degree of polynomial you intend to use. And then is an indicator variable trying to pick up treatment values of the outcome that belong to either treatment, because D is 0 and 1, right? So if D is 0, it turns this up, it's 1, it turns it down. So it's like it's first order polynomial. So that's what is here. And this poly function is the function that creates, I think, the rectangular window, something like that, inside where the linear model gets executed. Okay, so and then of course from the linear model, this is the term file. Then you pick up the coefficient, the estimates, and pick up the standard error, right? The diagonal of the variance covariance matrix, do the tests, and this is just putting out the result, and then the confidence interval is computed just before moving. So this is the p-value. This is the p-value. And then number of. So you just go along the loop and assign to each row and column each of these variables, all coming from the results you got from the linear model.
So it doesn't look like in this there's anything really super fancy going on with the standard errors. I mean, it's just literally estimating linear models with and looking at the difference at the cutoff and doing normal inference right there.
So because if you're reading this paper, they look so complex and mathematical that seeing the code and seeing what is going on behind really helped a lot. Please do understand it.
Yeah.
And in a very interesting way, okay, so I didn't know this. Even the randomization inference and all that, like the codes are just very similar. The differences are so little. I should run this page. Okay, so that produces the first table, and of course, this is the quadratic model, the same thing, right? But we increase P to 4 here, right? So it's going to give you the same results. Okay, let me run it in case it has something you're going to use in the future. Okay, so that is the placebo testing. And we just saw that chart. That will be. Okay, so that will be these values here. The values in it on the second panel. Yeah. So so this simply takes those values, and the commander talked about that, takes those values of the values you will not expect that that should have influence on, like your estimate should not be affected. So injury, the head start was not targeting on that, right? And the mortality rates before head start. So I see, look at the code of this, but just about the same thing, right? So you also just do your estimate your standard error, do your linear model, but the linear model will just differ slightly, right? Okay, here we're doing quadratic, so you're using 4, your PS4, but in place of your outcome will become replaceable, right? The variable you're choosing as your test variable, and then the other part of the model will remain the same. That's the way it is. So if we run that very quickly, just produce one of them and we move to the other part. It didn't produce the result. Okay, let's try that again. Okay, I know. I don't think I executed this. Okay, so we can do that now. We can only use that. Okay, so it gives you those p values on the lower section of the paper. The one that is here, 0.953, 0.31. Okay, so
Hey, you may got just like 3 minutes, couple minutes. I'd be interested in seeing, just kind of quickly running through the their RD robust.
Okay, so that's
I think that's just next, right? Yeah.
I think that is nice. So that is the non-parametric So again, this code are very similar. You're holding a place and then you're generating the table. So is the function here that does that, right? So if we look into that function,
it's like how many, it looked like running that before required that poly took several lines of code to do now what RD robust is doing.
Right.
For you, and you're entering in your outcome variable, your running variable, your polynomial order.
Yes.
What's Q?
This is the degree of what will be used to compute the confidence, correct the biasness in the confidence.
Oh, yeah, okay.
Yeah. So, and if we do this very quickly, we can see that. Yeah, we specify the order of local polynomial used to construct bias correlation.
Yep, I remember that now.
So like as I think I mentioned earlier, we just have the code, but the idea is just go in and study it more to know how it come about. But the functions are just one line, and everything, all the mathematics we were seeing on the paper is
They made it easy for you.
Yeah, it made life much more easier. So that is what the robust does, and then the robust does those bias corrections and all that. And if I should have 1 minute, if I should round up. So essentially this table, if I continue running this, going through all of this, at the end, it just produces the values we have on that non-parametric. Yeah,
Easy.
yeah, but it's and the same thing happens with the randomization inference, and I can skip to that very quickly.
Yeah, that'd be cool if you could just show that really quickly.
Yes.
Because I mean that command is super easy because you just specify, you just plug in a few values and you've got the results.
Right. And the only thing was anyway, we don't know the calculation going on behind, but for the fact that
Yeah.
at least from application point of view, it's becomes easy. So here is so this will take time anyway. This is the window selection, and this is the function that will print this. Yeah, so these two that is what is printed here. But the actual, this is for the plot itself to be printed out. But the actual code for inference, randomization inference, is right here. Okay, so this is the function that does that. Again, if you do question mark that function, it brings out all these inputs you have to provide. Yeah. So I guess the beauty of this is that we're not doing the integration or whatever complex mathematics to get the values, but at least we know what we need, the variables we need at that function. And knowing these variables you're putting in here gives you idea of what this function is doing, and it helps us understand what the entire thing is actually trying to do at the end of the day. So, yeah. So,
Yeah, I mean, that seems super easy. All you have to do is, so outcome, running variable,
yeah.
window on one side, window on the other, number of replications.
Right.
Yeah.
You only need to understand the value, the concepts themselves, so that
The
you need to
basics,
alter it. You know what you're altering and what's changed. But they did a lot. I mean, I think this will help apply research as a lot. You don't need to know so much of the technical details to be able to do this. Okay, I'm over my time by 2 minutes.
Oh, that was very helpful. May have to have you come to our club at some point.
Okay.
Do a art club session.
Yeah.
Thank you.
I
Did you share these slides? Sorry, I didn't even see your.
No, I was finishing just before class, so let me share that now as well.
Yeah, that'd be helpful. And don't forget to stop your recording.
Oh, okay.
Stop, yeah.
That's
Stop, no. Click on more first
okay.
and then go stop recording.
Okay.
And then it should say, and then say, yeah,